All right, I'm going to start, guys. Hey, everyone. I'll get started in a few minutes. I'm just going to wait for more people to join in. I'm recording this to post later, so I muted everyone, and we're not doing videos per BPS orders. If you do have questions, though, you can use the chat feature. All right, we'll be going over the conductors and insulators FET lab, so you can pull that up. Good morning. So you can pull that up, and along with the FET simulation itself. And so if you like, you can go along with us and enter in responses to the questions and do this while we walk through it, and also ask questions if you have anything that you're still struggling with. All right, so I'll get started in about 2 minutes. All right, so if you're just joining us, we're going to be going through the conductors and insulators FET lab that I assigned earlier this week. So you can open that up, and if you have any questions, use the chat feature as I'm going through. If you have any questions, we can discuss them. All right, I'll be using the attendees list to take attendance, but if you know somebody is not able to make it to this, then you can just watch the video, and I'll leave some instructions on how you can post, just add in a post so that you can be marked present. If you already finished this, you can review it with us, or if you don't have any questions, then you can check in and then check out. If you've already done it, I'm okay with that. I mean, if you've done this and you feel comfortable with the content, then, I'm okay with that. This is more just a help session. I know there are new rules around taking attendance and having mandatory Zoom sessions, but, I'm a little bit more lax on that. So if you just check in and check out, I'll count that as being here, and I'll record this. And if you watch the video and leave a comment, then I'll count that as having attended as well. Let's see here. All right, nobody else checking in for now. I'll add anyone if they show up. So the objectives for this are just to look around at household items and kind of see which items are conductors of electricity and which are insulators. And we want to differentiate between those items and better understand what they are and what that means for something to be a conductor and insulator. And so important questions to look at are how does electricity travel from one place to another? Which objects can be used to complete a circuit? Why do some objects conduct electricity and others don't? And so we're going to complete this document by filling in data tables and answering questions. And we're going to this simulation here. This is a PhET simulation. You're going to use the HTML5 because it's the only one that will run in browser. You click start, and then this simulation will load up pretty easily. And you want to do the intro because we're not doing anything really advanced at this point. We're going to continue studying electricity for the next few weeks. And so we'll probably touch upon this simulation at least a few more times. Okay. Let's see. Let's go on to the exploration phase. Make a circuit to light up a bulb using only wires and one battery. And then the questions are, how can you edit each part of your circuit? Can you add a switch? And how can you reset your screen? So these are just making sure that you can and are able of doing these things. So the first one being, all right, hello everyone. If you're just joining us, we're going over the Conductors and Insulators PhET simulation. And so once you click on the link, you're going to get to this simulation here. This is the PhET intro DC simulation. And I've already created a circuit in this simulation here. How can we edit the circuit? If you want to edit the circuit, there are special features. You can click on a connection node, click on the scissors, and that opens up the circuit. You can click on a component itself and delete it. And these are all ways that you can edit the circuit in the simulation. And so here I've made a circuit to light up a bulb. It has a battery and a bulb, and I can click on the battery and modulate the voltage. I can even click on the light bulb and modulate the resistance associated with it. And then here we have the household features that or items that we're going to explore. And basically we want to go through and categorize, are these materials that, you know, electricity will pass through and turn on the bulb, or are they materials that will stop the electricity and not allow electricity to pass through? And so if we do a paperclip, I mean, it's kind of obvious that paperclip will allow electricity to move. And we can see that by these electrons, simulated electrons, moving through the battery to the light bulb and then continuing around in the circuit. And you can even see small lines of radiation kind of emitted from the bulb. So that's telling us that electricity is indeed moving. All right, so the paperclip, you know, what I'll do is the paperclip here, I will move to this side, and we'll use this side to be for materials that conduct electricity, and this side for materials that don't conduct electricity. So now let's hook up the pooch, the dogs here, and if we look closely, we don't see the electrons moving at all. So dogs, as it turns out, are actually not good conductors of electricity, and I don't encourage you to hook up any dogs to any cables and test that for yourself, but dogs are not the greatest conductors of electricity. All right, so now let's try this hand. If I connect this hand, I don't see any movement from the electrons, and that's telling me, again, that the hand is not really a good conductor. The coin, if I add in the coin, we see some movement. If I add in the dollar, dollar's made of paper and cotton, not really seeing any movement on the electrons. And now the pencil. The pencil, we're connecting it to the graphite. So graphite is carbon. And the carbon in this case is not showing too much movement at this point. Yeah. So I'm going to put that over here. It's not really showing a lot of movement. So you can classify those materials in this table. Light bulb turns on for which of the following? Well, it turned on for the paperclip and the coin, and did not turn on for the dollar, the pencil, the dog, the hand, and the eraser. And then if I skipped one, then you could just go back and you can check it out and just mark your response on the table. So which items can be used to complete the circuit? Well, we already went over that, but just to review, the paperclip and the coin. Let's see here. What do all these items that light up the bulb have in common? Well, if we look at these two materials, you'll notice that they're metals. Metals are amazing conductors of electricity. And that's because when metals are in solid form, they really don't hold on to their electrons very well. What ends up happening is the electrons really flow between the atoms, just like in the ocean, just water flowing from one place to another. And it's very easy to apply an electric field and get those electrons to move from one part of the solid to the other. Whereas if you look at the materials on the right, the pencil, the dollar, the dog, the hand of God, and then the eraser, well then these materials have really tight affinities, high affinities to their electrons. So they're not really going to let them go or relinquish their electrons very easily. And so that's why you don't get the electricity moving through, because you would need to apply an immense electric field to rip the electrons from the atoms to get them moving from one part of this material to the other. Not to say it's not possible, because you can pass electricity through anything, just about, but it's just going to cost you a lot of energy to move electricity through these materials. All right, so let's see. So metals really are the best materials to pass electricity through. Some of the best metals to pass electricity include copper and gold. We would have more gold in circuits if it wasn't that as expensive as it is. And with that said, even copper, which is in most of our wiring in our homes, is getting more and more expensive because it's just harder and harder to find. And we also our lives are just saturated with electronics, so it's being utilized more and more. So it used to be not too long ago that we had copper pipes running water throughout our homes, but more and more we're using plastic because plastic's cheaper. Do you think you can light up the bulb with any other items in your home? And so just think about items that you have around your home and list those two items. And then here, why did you choose those items? And if we go back, what do all those items that pass electricity through them have in common? Well, we see these two items here. They're made of metals. And metals, again, are great passers of electricity. They don't present any barriers to that energy, or very minimal barriers. They have some resistance associated with them. Yeah, there still are copper pipes everywhere. It's still the standard because historically we've been using copper pipes for a long time. Anytime I do a renovation in my house, I still, even though it costs a lot more than plastic, ridiculously more, copper pipes, they last a lot longer. I think everyone's in. There are some problems with copper. Copper can corrode. Let's see here. So why did we choose the objects that we chose in 3? If I were to choose objects around my house that were great conductors of electricity, I could say the copper pipes, right? I could say my stainless steel drinking glass or drinking cup that my daughter uses. And what do those things have in common? Those things are metals, right? The easiest go-to for passers of electricity are metals. Hey, there's this cautionary tale, right? When I was a kid, my mother would not allow us to take showers during lightning storms. And anytime there's a storm, it's like, oh, no shower. I don't care if it's raining day or night, you're not taking a shower for the next week. All right. And if lightning strikes, and strikes somewhere in that plumbing system, then there could be a path of electricity to go from the sky, the heavens, through your pipe and plumbing, through the bathtub and shower, and then through your body and potentially kill you. If you have a question, just go ahead and post it on the chat window. see here. With that said, though, just because something's a metal, again, electricity can pass through just about anything. When I was in college, I went to the University of South Florida in Tampa. Um, Tons of afternoon lightning storms in Florida, all right, when it's nice and warm, especially in the spring. And there was a student, she was walking from the athletic center to Cooper Hall, which is where, all of our liberal arts classes are held. And as she's walking by this massive oak tree, the oak tree is struck by lightning. Lightning travels down the tree, gets to about her level where she was standing right next to the tree. Now, electricity always wants to travel through the material that presents the least resistance. It is not easy for electricity to pass through a tree. And you can see this. If you look up pictures of trees online that have been struck by lightning, those trees have been mutilated. Those trees have been, torn up. A lot of them get split in half. You'll see evidence that lightning was passing through. That lightning, once it reached her level where she was standing horizontally, her level, saw a new potential to get to the ground much more easily by traveling through her body. So what ended up happening, lightning went down to her level, jumped out of the tree, shot out of the tree, entered her body, and then went down into the ground through her. It flew her back. It shot her back about 10, 15 feet into some bushes. She had no clue what happened to her. Ended up walking back to her dorm and skipping class because she didn't feel well. Had some other symptoms that happened, and eventually she went to the hospital and they said, "Hey, you were struck by lightning at some point today." There's some sort of test that doctors can do to determine whether or not you've been struck by lightning. Okay, just checking for any new attendees. All right, the application. Let's see. Yeah, Mythbusters. Oh, fun facts, guys. Okay. I don't know. Oh, Mythbusters. Yeah, Mythbusters always a good show. All right, application phase. Objects that allow electricity to flow through them are called conductors. And so now that's where we're going to introduce this vocabulary of conductors. Conductors are materials that allow energy to easily flow through them, right? Just because, we are talking about electricity here, but we can also talk about this in terms of thermal energy. So conductors are a great sort of movers of energy. They can move thermal energy, they can move electrical energy. Whereas materials that do not allow energy or electricity to flow through them easily, we call those insulators. All right, insulators stop or resist the flow of electricity or thermal energy. We put on jackets when it's cold outside, and what that does is it insulates our bodies. It keeps the thermal energy that our body's generating using the food energy that we ate inside. It keeps it inside of our bodies. If we wore jackets made of metal, well, we wouldn't really retain that thermal energy for very long. All right, that energy would just sort of escape really quickly. And so analyze the data and place each item in the table below. So the conductors were those metal objects, the coin and the paperclip, and the insulators were basically everything else. They were the pencil, the dollar, the dog, and the hand. All right. Let's see here. All right. Click the button where it says Lab on your simulation screen. Make a circuit that lights up the bulb using the items from the table below. Use the brown and copper battery from the menu. Set the voltage to 1.5. That's already been done. Increase the voltage of the battery and record how the light is affected. Draw a picture of the light bulb in each box. You don't necessarily have to do this. One way you could do this is just grab a screenshot. All right. Command Shift 4 if you're on a Mac, and then just drop that in there. But you can also just tell me about the brightness level. Is the brightness low, medium, or high? I'm okay with that. All right, so what I'm going to do is for the low battery voltage, I'm just going to go through the coin, the dog, and the pencil. So I'm going to do those three. And so at 1.5 for the coin, we see that the brightness is low. So I'm just gonna put low. For the dog, the brightness is, okay, so there's no light. So no light. No light. And for the pencil. And for the pencil, no light. All right, so let's crank up the voltage. All right, so we went low voltage, 1.5 volts. 1.5 volts is low voltage. You could take a 1.5 volt battery, hook some wires up to the end, put it on your tongue. You'll feel a very mild tingling sensation. That's low voltage. It's not really going to cause any damage. The energy potential difference there is pretty low. Let's go to something a little bit higher. We will slide this up to, I don't know, how high does this go? 120. So let's do 50 volts. Okay, so 50 volts. All right, for the coin. All right, so it's pretty bright. So let's say high. So let's talk about the brightness in terms of low, medium, high. Pretty high brightness. The dog. All right, is this enough to fry a dog? Let's see. All right, what is that? We are at 50 volt. That's what I want to check. Dogs still no. 50 volts will not travel through a dog. So this is no light for Senor Pooch. All right. Let's see here. And now let's go to the graphene, the carbon. All right. Great. So we're actually seeing some light going through the carbon. Carbon is what's called a semi-metal, right? It can conduct electricity, but it does present quite a bit of resistance to electricity initially at low voltages. It takes a very high electric field or high potential difference between one side and the other of the material in order to cause electrons to shift or move or float or fly across that material. All right. In this case, the potential difference we're applying is 50 volts. So 50 volts is pretty high. You can actually do an experiment at home. If you have a battery and a small light bulb, you can take and draw a circuit on a piece of paper with a pencil and draw these lines here, hook up a light bulb on this side and a battery on the other, and you will actually get electricity that flows through the lines that you drew using the pencil. And that's because graphite's actually a pretty good conductor, especially when there's a lot of it. If you want to draw really thick lines where you can actually have the dust of the pencil kind of coming off and getting everywhere. Let's see here. Hold on. Okay, yeah. We're doing all right on time. So graphite, let's see here. Turns out actually has, let's put some medium light here. So medium bright. Yeah, there's tons of experiments and research being done on graphene right now and its use in circuits. All right. Let's see. And now let's go to high voltage. I think we can take this up to 120. 120 is the peak voltage coming out of your outlets. So hopefully nobody's ever had a bad experience putting a fork in an outlet. Don't do that. But this is the peak voltage that comes out of your sockets at your home. It has potential, a lot of potential. We use it to power obviously everything in our homes. So there's tons of energy. Look at that, very bright for the pencil. So, high level of brightness. The dog, let's see what happens with the dog at 120. So I'm gonna move the pencil to the middle because it's a semi-metal. It's a semiconductor, excuse me. or semi-metal as well, because it can conduct electricity fairly well in the right situations. The dog is still an insulator. All right. So apparently, if we want to keep ourselves from being shocked, we can wrap wires with dogs. We can wear dogs. Dogs are great barriers to energy loss. All right. You can wrap your dog around you when you go outside in a cold day, and it will prevent heat, thermal energy from escaping your body. The other thing is, if we want to prevent ourselves from being shocked when we touch a wire, we can wrap that wire in dog. All right, dogs are actually great insulators. With that said, other excellent insulators, because dogs are living creatures, we might not want to use dogs all the time, are rubber. Uh, Human flesh turns out not a great conductor as well. We can hook that up. Um, let's see here. And cotton and paper, right? Pulp. Rubber is pretty cheap to produce. Naturally, it comes to us very good. Cuddling dogs does help with depression. That's great. Rubber is really easy to produce. Rubber comes from trees. There are vast, vast plantations of trees in South America and in Asia that produce tons of rubber for us. So that's why we've been using rubber for well over 100 years to keep us insulated from electricity. Early on, though, we didn't really have a lot of access to rubber, so people would experiment with different materials. Asbestos, which is mineral mined from the earth. There's a town in Canada called Asbestos, which is the largest open pit asbestos mine in the world. So we get a lot of asbestos there. We used to wrap wires in these materials, these funky materials, before we really had clean access or consistent access to rubber. And they weren't always the best. Early on, we used to run wires, electrical wires, underground with these really shoddy insulators. And in New York City, there's some documented cases where you get a lot of rain, and this is in the late 1800s. You get a lot of rain, or early 1900s. You get a lot of rain, and the ground will get soaked with water. And underground, we had these electrical wires running, and it's over 100 years ago. But the insulators around those wires were really mediocre at best. We didn't have really nice, purified, clean rubber to wrap around them. And so you'd have, abuelita and the family maybe going home from church in the rain, on their horse and wagon. And horses have metal shoes. So here's the horse, going down the street, huge puddles everywhere. And then you have one instance or a few instances where there were breaks in the insulation around the wire. So the electricity is leaking out of that wire, and it wants to go towards metal, things that are easily conductors of electricity. And you have many cases where horses have been just electrocuted to death walking in the rain because of poor insulation, poor insulators that weren't sort of keeping the electricity, which is where it should be, in the conductor. Let's see here. All right, so let's see. The dog, no lights. Coin, we can try that, but it's sort of going to be obvious in this case. 120 volts, we should have a ton of light coming off of that thing. Yeah, ton of light. Yeah, but this is a problem though. I doubt anyone's house still uses these, but some people maybe still do, especially if you live in an older home. The last home I lived in was made in the 1880s. So, we used to have a system like this, but, there's some systems, instead of using circuit breakers in your home, it's the panel with switches inside. The predecessor or the precursor technology to that were called fuses. And this is a fuse right here. And what a fuse does is it allows only a certain amount. For some reason, that is just bothering me, how quickly that's going. But fuses only allow a certain amount of electricity through, or a certain amount of current through, before they just blow up. They don't literally blow up, but this wire inside just kind of burns out. Well, what would happen is these things would burn up, and you'd have to buy a new one, and then that one would burn up over time, and you'd have to buy a new one. And some people just got sick of replacing them. The fuses you use in your home are not bar-like like this. They're actually round like a coin, and a lot of them are actually more or less the same size of a coin. So what some people would do is they would, instead of buying a new fuse, they'd reach into their pocket and put a quarter into the fuse outlet. And the problem is, sure, that would work for a little while, but if you ever run too much current through that coin, you could melt the coin into your fuse panel. All right. It would get so hot also from melting and all that, you could start fires. So that's kind of a, an issue with the fuses. And we've moved to breakers, which, you don't necessarily have issues around excessive heat building up and fires or fire hazards. So this was high. So the coin at 120 volts had an immense amount of light. So look at your data, fill in the following table. Which ones are conductors or which ones are insulators? I think the only one we could move over to the conductors list from before is the pencil. We said it's a semi-metal, semiconductor. It conducts electricity part-time. So you compare the table above to the one you had earlier. Did any items change positions? If so, why? The pencil really is the only one that changed position. Let's check again. Yeah, it's the pencil, the only one that changed over. And again, that's because sometimes with the right amount of potential or voltage or a big enough battery, then we're going to get electricity to move through. Let's see here. And after comparing your results, how would you modify the definition of insulator? All right, so let's look here. Objects that do not allow electricity to flow through them are insulators. Do not's a bit harsh for that definition because energy can flow through anything. It's just how quickly is that energy going to flow through? So after comparing results, how would you modify the definition? Well, I would say it's not do not allow energy or does not allow energy to flow through. It just provides a great deal of resistance to energy flowing through them. So that's how I would change it. It just provides resistance. It more or less stops the energy from flowing or just reduces the rate of energy flowing through them greatly. All right, so we've gone through this. If you have any questions, I'm going to leave the next about 5 minutes for questions. If you're done and you've completed this, you're good to go. But just use the chat window for any questions, and we'll hang out for about 5 more minutes for the Q&A. Next week, we'll be looking at different types of circuits. So we'll be using FET to explore series and parallel circuits. And so get familiar with this, get comfortable with using this simulation because we'll be using this again. And there's a cool feature here that allows you to see what the schematic symbols look like for these objects. This is the symbol for resistor, a light bulb here, excuse me, a battery here, light bulb there, fuse. Most people don't use a symbol for a fuse though. If you have a question, you can just go ahead and post that in the group chat. I'll address it now, and then we'll be concluding the session in about 3 minutes. Well, it's not a matter about it being a liquid or a solid. It's about the presence of um, charge carrying uh, something that can carry charge. So in a solid, the electrons are there. They're negatively charged particles. And what happens is with the batteries, you have a positive terminal and you have a negative terminal. So if you're looking at the simulation, at the top you have a positive terminal and you have a negative terminal. And so with charges, we know opposites attract. So these electrons are flying towards the positive terminal. And so that's through a solid. So this copper wire is a solid. All these materials here are solids. So there's no liquids in this circuit. In the case of a liquid, you have ions in that liquid, positive, negative ions, that can also act like these electrons moving through solids. They will move through the liquid in the same way. So if you dissolve salt, NaCl, into water, the Na and the Cl will split, and you have positive and negative ions floating around in the liquid. And so if you put the two ends of the wire, if I were to open this up here and drop these two ends into a cup of water, then the electricity would still be able to float through because now the charge would move by using the chlorine ions to go from this wire to the other, the negatively charged chlorine. Excuse me. So as long as you have charged particles of some sort, you can get electricity to move. And it becomes a little bit more difficult in a liquid. You need more and more, you need a high level of ions present, and it becomes really hard in air because air is effectively a great insulator. And that's because the spacing between particles in the air is just so vast, it's so huge. And lightning can travel through air because its potential, the voltage is just so high, tens of thousands of volts. And great experiments out of the University of Florida in Gainesville, where they shoot rockets into the clouds during lightning storms, and those rockets are tethered to a spool of wire on the ground. They'll shoot the rocket. That rocket shoots up into the sky with a thin wire trailing behind it. Lightning strikes the rocket. The lightning travels through the wire to the ground, and what they've done is they've tethered that wire into the ground. And right where the lightning enters the ground, there's just so much energy that it melts the sand and creates these glass castings of lightning. And if you go to the Museum of Science here in Boston and you go see the electrical show, when you're facing the stage of the electrical show, on the left-hand side, there's a cast of one of these glass casts of lightning. I'm not sure if it's from UF or not, but it's beautiful. All right, any other questions before we part ways? I'm not on video. I'm on audio only. Yeah, more or less similar, exactly, similar to Benjamin Franklin's lightning charged kite experiment, right? Yeah. All right, that concludes our session today. If you were in attendance, I'll mark you present, but if you're not here, if your kid's not here and they watch the video, I'll still mark them present. All right, have a great day, everyone. Hope everyone's doing well. If you have any questions, please feel free to reach out via email. My daughter wants to say bye. Go ahead.
Bye.
All right, there you go. All right, take care, everyone.
Oh, that's perfect timing. All right, let's see. Hey, Bug, do you want to buckle in? Yeah. Oh, boy. He's trusting you so much.